Thanks for the introduction, Johannes, and thanks to Josh and the committee for inviting me to do this. This is a nice opportunity for me to expose some of the things that we're doing at Haystack, but really in a lot of places around the world. It all has to do with using radio, either passive, so that's radio astronomy, for example, or active, radars for looking at the ionosphere. And I really enjoyed Sharia's keynote yesterday. He was looking really small. He was talking about ASICs and small things. So I'm going to kind of reverse that. I'm going to start really big and then kind of gradually come closer to the planet and then go down to smaller things that I hope to end with a little bit of stuff that in fact has GNU radio in it and that has opportunities for people who are interested in radio and information transfer to actually participate in. So we'll see how this goes. So I come from Haystack Observatory up in Westford, Massachusetts. This is a overhead helicopter shot of our little hill. We have 1,300 acres, which is a large amount of land in eastern Massachusetts that's still undeveloped. And as part of that, we've been there since the 1950s, doing essentially fundamental either radar or radio, in this case, and in these days, both observations. You will see from the size of that photograph that we have some reasonably large antennas and large systems up there. When we were put together up there, this was where people from Boston went to have their summer homes, if you can imagine, given the density of population in Massachusetts. So it was built in a place where there weren't too many people around, so if you had loud transmitters, and I'll talk about loud in a minute, you didn't really bother them. Of course, now we have people living all around the observatory, but that was the reason it was established. In the upper right-hand corner, you're going to see a little diagram with kind of two arrows. Essentially, Haystack Observatory is operated by MIT campus, which of course is not out in Westford, Massachusetts. It's about, 50 kilometers away from the Cambridge campus where, all of MIT's activity, or most of it goes on. So we do fundamental research, we publish papers, we talk to folks here, we give conferences, and we operate the site. But on the site, there is also that right-hand arrow, which is MIT Lincoln Laboratory has a bunch of radar sensors there. And the way MIT works is that, sensitive classified projects are segmented off into Lincoln Laboratory, which is in Lexington, Massachusetts, about midway between Cambridge and Westford. And that is the site is part of the Lincoln Space Surveillance Complex, which does things like keep track of objects, in the catalog, in near-Earth space and geosync and a little beyond. So we do a bunch of different things there. And of course, just to be confusing, there's a lot of different names there that for the different pieces of what is really Haystack Observatory. As I mentioned, we actually do a lot of different things that essentially are applying radio science or radar science to remotely sensing the universe, to Earth, and you can see some of them on the left-hand side. Really, the left-hand side is the science research we do, and the right-hand side is the fact that we also concentrate on a lot of technology, which is, of course, is married with the science application. I'm going to talk today essentially about radio astronomy to start with, and then some atmospheric science, essentially ionospheric measurements, but I could give another talk on geodesy, which is how you figure out how the Earth is oriented and what the clocks are on Earth relative to the celestial sphere. Space science, we're doing some flight projects these days. Polar science, I have a colleague who's doing cryosphere work and looking at ice breakup in the Antarctic and that sort of thing. It's obviously all underpinned by data science and informatics, which is, of course, the lingua franca these days. And on the right-hand side, you can see the technological places that we concentrate on. Radio arrays, very long baseline interferometry, something called incoherent scatter radar, which I'll talk about in a little bit, and then, of course, as I mentioned, space science. Obviously, we're all here at GNU Radio because we enjoy using the electromagnetic spectrum at radio frequencies, and this is just a reminder of the fact that, science is using that whole stretch of electromagnetic spectrum, but of course, it isn't just science, and as everybody knows in this room who's been playing with communications, for over 100 years now, this spectrum has been heavily used for human purposes, for communications. These days, precision navigation, timing, distribution. And so we're actually fitting our science in amongst all of these. As you go up higher in frequency and you get to, centimeter wave and millimeter wave, used to be that that was fairly empty except for science use. Of course, now with the advent of devices that work at those frequencies, there's a bit of a coexistence issue developing, and that's one of the reasons why science actually has to work very closely with the technical community to sort of cooperatively share the extremely precious electromagnetic spectrum. And this is just one reason why we might want to pay attention to that. It turns out that if you look at, for example, a galaxy pretty far away, that's the Whirlpool galaxy in the middle. If you look at it in the middle in optical, well, there's a lot of dust. And so you can actually see the spiral arms of the Whirlpool galaxy, but it's a little hard to see what's actually at the center. As you go to longer wavelengths and you get into microwave, for example, and in the infrared and into radio, the spiral arms of the galaxy begin to represent themselves, and you can start to see where matter is coming out. And if you combine that with even shorter wavelengths than optical, like ultraviolet or X-ray, the point is that the combination of all of these different wavelengths or frequencies in the EM spectrum is the way that you can synthesize the life cycle and the physics of the object. So it's important, I'm going to concentrate on radio, but it is important to look at all of these different wavelengths and talk across communities to figure out fundamental information about how these systems are created, how they evolve, and how they die. There are, as I mentioned, there's natural sources of radio emission everywhere. If we think about radio astronomy, Jupiter is the loudest thing in the solar system at decametric wavelengths. And the sun, of course, is a very bright radio emitter. You go out to the Milky Way, you've got star-forming regions, old stars, things blew up, supernovas and remnants. You really can see now an enormously varied bunch of stars, white dwarfs, distant suns, infant stars. All of these are generating, for example, radio at some point or another. You go beyond our galaxy and you're getting the quasars and radio jets, which, as we'll see in a moment, are a very, very powerful remote sensing tool. And if you like to do astrochemistry and figure out, okay, in the cloud where a star system is beginning to evolve, what's there? And it turns out by looking at the background, cosmic microwave background radiation, and looking at notches in that, you're kind of doing a form of a spectroscopy. And you can actually use those particular notches in your knowledge of chemistry to figure out that, for example, methanol is over there, or ammonia. And in fact, there may be a methanol maser at some point where you actually have a resonator that's producing a particularly bright line with an absorption signature that must be methanol. So you can actually do astrochemistry and explore the universe without having to inconveniently get into a ship that doesn't exist yet and travel, 1 million light years away. If you'd like to learn more about that, by the way, there's a very nice podcast from my colleague Lynn Matthews at Haystack. I will leave these slides. You can either grab the URL or hit the QR code there. One example, by the way, of all of this is how do you weigh a star without having a scale and a place to put it on? Well, one of the things you do is you look at neutral hydrogen, which happens to have a particular energy transition, which emits a photon at L band. And that gets redshifted to lower and lower frequencies. So you look at the rotation of those emissions in radio, and you can actually work out what the weight of the star would have to be. So quite cool, and a nice example of remote sensing. Here's a really interesting one. How many people have heard of black holes? Of course you all have. All right. It turns out that more than 2 decades ago, people at like UCLA at the Keck Galactic Center Group made this movie I'm going to show you in a moment. There are all of these stars which you'll see with labels. So and the date is in the upper right-hand corner. So we'll start running this. And these are people just measuring the orbits of stars. There's obviously something really, really heavy in the middle that's causing a star to get warped out of its orbit. So that has to be, according to physics predictions, there's probably a black hole there. In fact, we now posit that there are black holes at the center of nearly every forming galaxy. But all we know is an indirect measurement before about 2019. You saw you had to measure this over 20 years. You watched the star slowly evolve its orbit. So the idea was, could you go farther? Well, it turns out that you can. By the way, this is another image of a place called M87. This is Messier Object 87. And if you look at that galaxy, there's actually a jet of material that's streaming out from the center. So something has to have had enough dynamic features to actually take all that material and eject it in a stream. The idea, though, is there must, again, the theory was, well, I bet you there's a black hole there, and I bet you the black hole is squeezing matter so much that it's actually ejecting the matter into this jet. And that could be a fundamental part of how galaxies are forming and how star systems and planets and what have you are forming and how the material is distributed. This is from the Hubble, by the way, in optical. Now, it turns out that a black hole is a really cool object where if you get close enough to the black hole, even relativity breaks down. But if you get close enough, weird things start happening. So this is a nice little video. We're now kind of zooming in here on this particular, I think this is an M87. So here we are zooming in, and you can see that there's material in the interior that's really swirling around something that's, again, massive enough to make it orbit, kind of circling the drain, if you will. You can see that jet stuck there. And if it's so massive that even photons are getting warped out of their orbit. They're orbiting the black hole. They're getting tugged. So from our point of view, if we receive these, for example, photons at millimeter wave or radio frequencies, we're going to see something that looks like a toroid. That's all of the light being bent out from back of the black hole and forming a ring. So, geez, there's something maybe we can detect, right? That's radio emission. It's actually, again, photons and other electromagnetic radiation being warped. So how to do that? The problem is it's really tiny. Really, really tiny. So we can go through angular size, right? There's a protractor. We can take a degree, which is 60 arc minutes, which is 60 arc seconds, and we go to 40 to 50 micro arc seconds of angle. That's, again, like our little apple or orange on the moon as viewed from here. So that's a very, very small object, and you really want me to get some kind of detail about what's happening around that object. By the way, this is one of the closest black holes, the one at the center of our galaxy, Sagittarius star. There's a black hole at the center of our own galaxy, because we're like a lot of other galaxies. So just to give you a kind of a feeling for what that's like to measure, this image was taken by my colleague Colin Lonsdale. It starts out on a hill. It's about 40 kilometers or 25 miles away from the observatory, and we'll zoom in to show you the scale of what we're trying to measure with this particular something called the Event Horizon Telescope, which we'll tell you about in a minute. So here we are on Pac-Monadnock. There's the Boston skyline. You will notice this particular egg coming up. That's the Haystack radome with a 37-meter telescope in it. And then eventually, there's my colleague Jason Suhu. Okay, Jason is looking rather nice. It's a nice day. Jason has an eyebrow. Let's go find Jason's hair and his eyebrow. Let's keep on going. Okay, there's what we're trying to measure. Now I'll back out. That's the angular size that this telescope is trying to resolve. Quite challenging, but as, in fact, Sharia said of other things yesterday, even though it's astonishing and we're orders and orders of magnitude, people persisted and said, well, can we do that? So this is the Event Horizon Telescope, which is not one telescope. It's actually a collection of telescopes borrowed for the purpose once in a while. They're not dedicated. All over the planet, and the idea is to form a large telescope array with really good maser quality clocks that lose a second every 10 to the 15 seconds, or a second every couple million years. They're very stable. You have very stable clocks, and you measure at millimeter waves, and you measure a very, very long distance between one telescope and another, like the diameter of the planet. And if you work out, that's gigawavelengths. So this is a gigawavelength interferometer arm translates to a thing that is of the angular size that I just showed you. In fact, this is the highest resolution you're going to get because, again, you have millimeters, and you're able to measure not only amplitude but also phase. Phase is key to an interferometer, and you're doing it on thousands of kilometers of diameter. So you connect all these things together, and you can form a telescope that can observe the emission from that tiny, tiny thing and even try to derive some structure around it. This is what it takes. 300 members, more than 300, more than 59 institutes, more than 18 countries, North, South America, Europe, Asia, Africa. You can't do this alone. It needs a global community by definition because you're using the entire planet. So if you do that, the EHT is a collective, and Haystack is one part of it, okay, has imaged 2 black holes to date multiple times. The first one is an M87, which is in the Messier object. Now you might think, wait a minute, that's actually 55 million light years away, and you're starting with that one? Well, it turns out it's much, much heavier than the one that's closest to us at 6.3 billion solar masses. So think about 6.3 billion times the size of a sun in a very small package. But it doesn't change. It's relatively stable. So as the planet rotates and a telescope comes into view and comes out of view, you can actually image that where it's the picture of the thing you're trying to take on that particular time scale is relatively stable. So they started with that because that black hole is heavy. They moved on to the more challenging one, which is in the center of our galaxy, Sagittarius A star. That's only 4 million solar masses, so we're now a factor of 1,000 lighter. It's only 25,000 light years away, okay? But the emission is variable. The matter around it is actually changing. So there was another set of imaging techniques that had to be developed to deal with that. And down on the bottom right-hand corner, you can see these 2 kind of famous orange donut measurements that were made. These are our best guess at what the image looks like, consistent with the relative limited number of points we have from this particular interferometer. The key step, and going back to radio processing, is correlation. You're taking 2 telescopes separated by the diameter of the planet with really, really good clocks. You're sampling them at very high rates. I'll tell you about that in a minute. And then you're bringing them together, and the correlation process basically is the thing that not only forms the image, but tosses away all the other signals that were at one telescope or another, but were not the common signal that the telescopes were looking at. And that process is the way that you actually form the image. You can keep going with this. For example, in the left-hand corner there, you first visit, for example, M87 in April 2017, and then you visit it again 1 year later in 2018, and you see that there is some rotation, but in reality, the emission's remarkably stable. So this checked one box about how black holes behave. There's a nice little factoid there that M87 eats 1 mass the size of the sun every 1,000 years. That's actually a relatively stable black hole. Many of them are very messy eaters and eat more than that and dynamically change and grow. Not only if you want to find the emission, but you also want to find out what the magnetic field is like around this really, really intense object. You can get computer people to make simulations, which is the upper right-hand corner of M87, in polarized radio. And you can find out that the magnetic fields should be all twisted up. That's a model. This is reality. So in March of this past year, the image was happening with polarization, which is kind of like climbing to the top of the mountain. If you can keep your telescope's polarization calibrated, absolutely, because this signal, again, is so faint, you do anything wrong to it, it's going to go away. Now you have an image that actually shows you these very intense wrapped magnetic fields. So you're beginning to figure out the features of one black hole. Well, we've imaged 2 so far. There are many, many black holes throughout the universe. There's a zoo of them. Some of them spin, some of them don't. What's the spin? Do they wobble on their axis? What's the mass ratio? How does that relate to the size of the developing galaxy? There's all sorts of things you can find out by taking this really distant object and receiving these really faint radio photons. So we have fun doing that. And in reality, I mean, it's really leading to metric tests of general relativity that are just not accessible to weak field tests like anything we can create here on Earth. Creating 6.5 billion solar masses in your typical laboratory is hard. But here you can actually do that. And so this is really the dawn of a new era of black hole astrophysics. And just to leave you again a scale, that's the M87 image. And you can see there, for example, there's our solar system kind of stuck in the middle where the black hole would be. Remember, that's not the black hole, that's the material circling the drain and getting really hot and emitting all sorts of radio photons. So the scales kind of boggle your mind, but they're there. Now let's talk a little bit about hardware. We have to have very fast recorders. Here, you're looking at a Gaussian random object, so you're actually not looking for a lot of dynamic range. This sampling is really typically done at maybe 1 or 2 bits. But you want to run it as fast as you possibly can, because more bandwidth equals, the bandwidth that you run it is inversely proportional to the fidelity of the image. So higher bandwidth is more capable images. These are some of our recorders, specialized things. You can see the recording rate for the EHT, rather than a 2 to 4 gigabit per second kind of recording rate, which is typical for a typical VLBI experiment, very long baseline interferometry. The EHT is at 32 gigabits, 64 for 28, and the idea is to go to 192 or 256 gigabits consistently. So you can think about a couple of bits times, that much bandwidth on a continuous, a coordinated set of large telescopes. There's about 12 orders of magnitude in the data reduction. You start out with petabytes of raw IQ at a given center frequency at millimeter wave. You correlate it, now you're down to terabytes. You calibrate that, you throw away more information, now you're down to megabytes, and the image itself, it finally is, it would fit on your computer 20 years ago. It's about, 30 kilobytes or something like that. There's my colleague standing next to some of the data arrays. We still ship around sleds of hard drives. It turns out that it's still not fast enough to get it back on networks. We have to, a box of drives on a 747 is the fastest way to get data here per wall clock time. So we still ship stuff around everywhere you can think of, including from the South Pole, which is fun because it takes, 3 or 4 months for the ship to get here with the data, so people get a little nervous. But in any case, you can see the amount of data reduction. It's kind of staggering. I can't give a talk about this. There's a whole, literally conferences on this. How do you do this thing? Well, you have this image that you want to measure. You're really taking Fourier domain samples of it, very poorly sampled because you don't have a planet dotted with telescopes. You're forming all of these baselines, which translate into a 2-dimensional Fourier transform of the image on the sky. And then that should have been an animation, but you let the planet rotate. And you let telescopes come into view and then set, and you combine all that data together. So there's a whole special issue on how this is done, and that's still a very, very evolving picture. So this is kind of what's underneath making that image. Okay, we were really, really far away and really, really massive. I'm going to come back to the planet now, so we're kind of at medium scale. My background is actually as a geospace research person, so we do have a neutral atmosphere on the planet. You're breathing it from the ground, and it falls off, through the stratosphere at 7 degrees Kelvin per kilometer, and the atmosphere is getting thinner. And then you get up into the stratosphere where you've got wave activity, and so the temperature goes up some. You then get into the mesosphere, and you get to about 85 or 90 kilometers up, which is the coldest place in our atmosphere. It's actually 140 Kelvin up there, and this room is 270-something Kelvin, so you can think about that. And then it gets hot again as the atmosphere gets thinner for wave activity. The sun illuminates all of that with extreme ultraviolet photons. They're so energetic that they start ripping off electrons from the neutrals and they make ions. And the reason that we have had transcontinental communications way back to the 1920s is the ionosphere that surrounds our planet. At this planet, we have a weakly ionized atmosphere. There's about 100 times less ions than there are neutrals. But it's a plasma. You have ions and electrons, and they don't just go right back together and form neutrals again. They are separated by electric and magnetic forces. And so between day and night, you get different layers of the electron density as you go up in altitude, and you get different ion compositions. The atmosphere is gradually getting lighter as you go up. And there's all sorts of dynamics in there, and it turns out that is something that we study at the observatory and in a whole community of people around the world that deal with this from a fundamental physics point of view. But it's not only fundamental physics, there are a lot of applications. As we all know, we're inexorably going to a spacefaring society, and one of the consequences of that is to have to understand the environment that you're in and how it's affecting systems. That environment has weather, it has storms, beyond the climate, much like the weather here on the ground. There are 2 kinds of categories. There's external forcing, the sun emits a coronal mass ejection with accompanying very intense magnetic fields, and we get a geomagnetic storm. The Earth's magnetic field gets disrupted. You might get a burst of X-ray output. That's a solar flare, which ionizes temporarily the D region in the ionosphere and causes an HF blackout for maybe about an hour. There's also internal forces. It turns out that we've realized over the last decade or two that the neutral atmosphere, and literally the meteorology, is actually coupled to weather in the upper atmosphere at well beyond where the astronauts are flying around in the space station. You have to kind of understand the whole system as a coupled unit. So feedback, regulation, all the things that honestly biologists study, we're having to study in this particular environment. And then there's the applications like, okay, did we disrupt GNSS for a little while? Did we manage to tell aircraft people not to fly a transpolar route for the next little while because of enhanced radiation exposure? That sort of thing. So space weather is a societal thing as well as a fundamental physics thing. So in New England, we're conducting this, just in case you need an orientation where we are. That's the map of New England. The little red, pointer there is Haystack. And if you went to Google Earth and you looked us up, you'd see an overhead shot of what I showed you at the beginning. We study all of the variations of the upper atmosphere, specifically mostly the ionized part, of the neutral part as well, at mid-latitudes. Why mid-latitudes? Well, a lot of people live at mid-latitudes, including this country. It is actually less studied historically. Most of the study, until 3 or so decades ago, was concentrated either on the equator, where there are a lot of embedded irregularities at wavelengths that tend to interrupt communications, or high latitudes, where things like the aurora happen and where particle input is coming in more directly from the overlying magnetosphere. This is work that we get sponsored by writing grants to NASA, National Science Foundation, Air Force Office of Scientific Research, Office of Naval Research, other kinds of things. So we're kind of out there slugging it out with the rest of the community to make a compelling case to provide funding. There's a reason to understand it. I pulled that yesterday. That's a website called satellitemap.space. That's actually a nice website. It's interactive. You can drag this thing around, and you could actually put your location in and see what the density is. That's the Starlink constellation as of yesterday. That's 550 kilometers altitude for almost all of it. There are 4,746 active satellites, and there's 6,949. And we could have a whole talk about the commercial use of low Earth orbit. What I will leave you with is that Starlink is licensed for 12,000 birds. They are applying for 45,000, and they are one of about 10 companies that would like to do constellations of this density or larger. So low Earth orbit is getting really crowded, and it's imperative on us as a society to understand what the environment that they're flying in is, and how the dynamics of that environment might affect the constellation and vice versa. So what do we do from the ground? Well, at Haystack, we do a rather specialized form of remote sensing using a fairly large antenna. Set of antennas. You can see on the left-hand side there, if you really got really good eyes, you can see the pickup truck parked at the bottom of the steerable antenna foundation. We have a radar at UHF frequencies. It's about 440 megahertz, 68 centimeters wavelength. And we use two antennas. One of them is a 68-meter antenna, 220 feet. So what's a soccer field? About 100 meters. So think about an antenna about 2/3 the size of a soccer field. And then the other one is a little smaller, 150 feet or 46 meters, but it's fully steerable. We can point that from the Canadian Maritimes to Iowa down to little between Florida and Puerto Rico and out into the middle of the Atlantic. So we have a very large field of view. So those are antennas. They're very efficient collectors of radio waves. But we have to make the radio waves because the ionosphere, in this case, that we're trying to sense doesn't really emit it, kind of unlike the radio astronomy I talked about a little earlier. So how do we do that? We use these. These are my transmitters. Those are high-power microwave amplifiers. Those are four-cavity klystrons. Klystrons are developed in the 1930s by a couple of different clever teams. Those put out in tandem to 2 megawatts peak. So we have a 2 megawatt flash bulb at UHF, and it's got a duty cycle of about 6%, so we keep it down to 150 kilowatts average to make sure the tube survives. Those are surplus from the Air Force's ballistic missile early warning system, for which the design parameters were almost the same as to detect the ionosphere. Physics worked out. That's our on-off switch, because you have to take up to 120 kilovolts at 4 amps and apply it to the bottom of the tube or remove it. So you need all sorts of high voltage bus work in an oil tank, 5,000 gallons of dielectric oil, because you don't want to create lightning bolts in the room. And you do all of that to make a very, very bright signal that you feed into one of those antennas. By the way, there's our waveguide. The UHF waveguide is the bigger one. It's kind of like HVAC duct. There happen to be some other ones at S-band and L-band, and one of them at KU-band, I think, in there. And then there's a little tiny one at W-band for comparison, but we use the bigger one. You can do this, by the way, not just with a mechanical antenna, but you can do it with a phased array. Sharia yesterday showed a lithography printed array with 256 elements. This is a UHF array with 4,096 elements at 2 megawatts peak, 500 watts per element, 4,096 element. You can see the people. If you find me in the picture, come find me later and I'll give you a prize or something. But you can see the scale that we're talking about. And the picture is a movie. The beam is scanning right now. I'm kidding. Because you can't see the beam and it's electronically steered. So rather than mechanically having to move the beam around, you can basically do the electrical equivalent of focusing the beam in different directions, much like the phased array that you saw yesterday. So we can use this. In this case, this is up near the border between the subarauroral ionosphere and the auroral zone to do more physics, but it's the same kind of technique that we actually do at Haystack. This is what we're looking for, a really narrow, it's only, in this case, one of the emissions we're looking at is only 10 to 15 kilohertz wide at UHF frequencies, but it's really, really weak. I take a megawatt class pulse and I pump it into an antenna with 42 to 45 dBi gain, so I'm at a few tens of gigawatts ERP, and I get back 10 femtowatts. Why? Because even with a box of electrons, each electron is a tiny, tiny object from a radar scattering point of view. But believe it or not, beginning in the late 1950s, receivers got sensitive that you could detect this. And there's an enormous amount of fundamental physics that you can use to remotely sense the electron temperature, the ion temperature, the velocity, the ion composition, and the electron density by measuring that little double-humped kind of shaped spectrum around the center frequency that you transmitted with your bright flash. So we can do this as an operational technique to actually do space weather or ionospheric measurements. Here's an example of what the spectra looks like. On the left-hand side, you see its frequency plus or minus 50 kilohertz, and then that's range away from the antenna, which in this case, because it's our vertical beam, is equivalent to altitude, and the space shuttle is flying about in the middle of there. You'll notice that the spectral shape does change as a function of altitude. That's because the temperature is changing. The electron density is changing. The composition is changing. You can take all of that, run it into a first principles plasma physics theory, which some extremely clever people with pencils figured out originally, and you get that. That's a map of the electron density above the ionosphere, above the Millstone Hill in eastern Massachusetts, over 24 hours. About sunrise is happening about in the middle. And the top part is the F region from about 150 kilometers to about 600 kilometers. Remember, the space station's flying in about the middle of that. And the bottom is is a zoom in at about 100 kilometers altitude for a reason I'll talk about a little bit later. So this is fundamental things that I can hand to somebody who is just doing ionospheric physics or ionosphere magnetosphere coupling, and they can take this and then do fundamental physics with it. We do that too, but we also do the remote sensing. So this is really powerful use, again, of radio waves. In this case, okay, we got to make the radio waves that we want to sense their changes when they come back, but it's a really nice way of remote sensing. How do we do this? Well, this is a paper that we published back in 2005, but it was actually something that we began in the late 90s. This is the software patterns that one uses to make not a hardware radar, but a software radar. And so we had an early idea that if we multicast, for example, some of these samples coming off the receiver onto a bus, we could then run various software patterns, reduce the data to some intermediate level, put it back out on the network on a different multicast channel, and then go that way. And so we've actually been using the multicast standard for quite a while. Now, because this was written in the late 1990s and early 2000s, a lot of this was originally written in C. I don't want to tell you how many times I sat there figuring out why a pointer had gone astray. I don't want to ever do that again. But remember, though, that we could do this on workstations because of the narrow bandwidths compared to some of the other bandwidths that we're talking about, for example, for the Event Horizon Telescope, which are at a whole nother scale. So very early on, we wanted to think about software patterns, which is exactly what GNU Radio is about. Software patterns, reuse, how can you then trade that with other people and have them do different things with it? So we've been thinking that way for a long time, actually. So I want to end today by basically then going even smaller. So I just showed you this big thing, you know, the electricity bill is about $100,000 a year, you know, the facility takes about $2.5 million per year to run. You're not going to go out and buy that at Target. What if we can do even smaller sensors that still receive fundamental ionospheric information, for example, and do it in a different way than the professional systems? So what I'm going to talk about is the work of my colleagues Ryan Bowles and John Swoboda, both at MIT Haystack. They presented a little bit of this at, for example, the New England SDR conference. So if anybody was there, you might recognize a little bit of this. But the idea is a much smaller system can do really kind of a serendipitous measurement. This is a picture, for example, from a McMurdo station down in the South Pole. If you want to measure the neutral wind in the upper atmosphere, not the ionized part. The ionized part will respond if you send a radar pulse because it's an electromagnetic wave, charges, they accelerate, you get a little wave back. The neutrals don't do that. So how are you going to measure what the neutral, for example, wind patterns are doing? Well, happily, nature provides meteoric dust as we orbit in the lane around the sun. And so every day we get many, many little tiny grains of micrometeoroids burning up. They leave a little ionized trail behind. That trail is a tracer, and it drifts with the wind. So if you can actually get a specular echo off that trail and watch it drift, you can derive what the neutral winds are going in a way that's very, very difficult to do almost any other way. You can try to do this with smaller and smaller systems, and that's one of the things that Ryan at Haystack has been pushing. Why is this important? Well, there's another diagram of just the temperature structure in the neutral atmosphere as it goes up. And you notice two arrows there. That's about the region that these meteoroids burn up, between 120 kilometers and about 80 kilometers. Those trails last for anywhere from a second to tens of seconds, and then they kind of diffuse away, and then another one comes along. This is critically important to understand the electrodynamics of the way this atmosphere goes. Because as we go from way up in altitude, lower in altitude, when we reach 100 kilometers, we reach this magic layer. It's really only about 10 kilometers thick. At that layer, the electrons are still stuck to our magnetic field. We have a strong background magnetic field in this planet, and so the electrons are stuck, but the ions are beginning to collide with the neutrals, enough that they actually get dragged off the magnetic field line. Minus, plus, electric field. So above that, both the electrons and ions are magnetized, and they kind of move together. Below that level, both the electrons and the ions are collisional, and now we're back to just collisional fluid mechanics. But in that nice little narrow region, you can get all sorts of currents flowing. So sensing what the neutrals are doing is just as important in that layer as sensing what the ions are doing. But it's unfortunately, try to put a satellite at 100 kilometers and see how long it lasts. Not very long. The energetics are terrible. You can shoot a rocket through it. You get one pass up and one pass down. You can't sit there and monitor it. So meteor trails represent a really attractive way, and this has been known for decades, but now the technology has been evolving such that you can do this multi-statically. And anybody that has looked at MIMO networks, you know, the routers in this room, these are very familiar patterns. You send a phase-coded technique where you make sure that the pseudorandom codes are all orthogonal to one another, so I can send multiple transmissions at the same time and not confuse that transmitter with that transmitter. And you can basically do the cross-correlation between all of the combinatoric pathways, and you can do interferometry. So you can localize that meteor trail, and you can watch it move. And you can then derive the velocity, which is what you're looking for. There are various configurations. You know, you can, if you have very good eyes, you'll see there's SIMO, which is single in, multiple out. One transmitter, put a bunch of receivers out, they're all listening to that single transmitter. There's MISO, like miso soup. You put multiple transmitters in one place, then you have a single receiver, but it can see every individual path from every different PRN code. Eventually, you get to MIMO. You have multiple transmitters, you have multiple receivers, each one that can receive all of the different transmitters, and the combinatorics start piling up, and you can get much more dense information of what's going on. So you can trade off how to implement these things. You know, it's much harder to give someone a transmitter in their backyard than it is to give them a receiver. So sometimes you want to concentrate your transmitters in one place where you control it, and then you can put your receivers out. For example, I've got one in my backyard, as I'll show you here, and I have a dog, and I don't worry about the dog kind of like touching the wire when something is being transmitted. So this is a very flexible and adaptable technique, and it gets to pull in all the MIMO techniques that people, for example, in this room and in other fields and in radio have seen. So there's a network called Zephyr that Ryan is developing, and the idea is, again, do the combinatorics, and the great thing is that you also don't have aliasing, like did that thing come from this altitude or twice that distance. With doing all the combinatorics, you can resolve those sort of ambiguities. And you can end up getting a three-dimensional wind field. So not only is it a function of latitude and longitude, but also of altitude, which is really important for the physics. This has been done a couple of places. There's been a prototype out in Colorado with our colleagues at CU Boulder. The idea is one transmitter site with about a 5-antenna array, and then there's also some other ancillary receiver sites. The thing is working well, and we're also standing one up in New England around that larger radar to be able to, again, put more than one piece of data on the same table and do physics that's consistent with all of it. These are the scientific outputs. I won't go into it except for to say on the right-hand side are meteor counts as a function of time. And you can see that they come and go because the sporadic micrometeors coming in have some patterns, if you think about it. For example, in a day, when we're at 6 a.m., the planet is rotating into the stream of micrometeoroids in our orbit, so that the numbers peak. At 6 p.m., we get a low number because we're whirling away from them. If you think about the way now the planet is rotating opposite to where we're at a place that's going opposite to where the orbit velocity is. This, again, derives stuff that's almost unavailable with any other technique. The derived winds, for example, for an example measurement, are given on the left-hand side. That's a square about 5 degrees by 5 degrees in latitude or longitude, or about 550 kilometers by 550 kilometers. You see all that structure? By the way, the left-hand one is one altitude, and the right-hand one is another altitude. So first of all, the altitudes are not behaving the same because of some of this coupled dynamics. And the other thing I will tell you is that one of the best meteor wind field has one vector in that entire thing. I would tell you that maybe there's a lot more structure than just one wind vector across that 5 degree by 5 degree box. So this is really fundamental information that you really can't get at almost any other way. So we're trying to apply some of the technology in this community, for example, and others to try to do this more efficiently with small systems. And finally, I'll talk about something that my colleague John is doing, which is an active technique. If anybody's heard of an ionoson, this is the way to do active sounding of the ionosphere at HF frequencies. This is literally the oldest radar technique there is. Gregory Bright and Merle Tuve on the left-hand side there basically invented this in 1928. There's a nice paper that shows that. You essentially send a wave from the ground up at HF frequencies, so between 2 and 15 megahertz approximately. When that wave gets to the point where it's equal to something called the plasma frequency, which is a fundamental resonance that's related to the square root of the electron density, the wave basically completely interacts with the background. The index of refraction goes to 0 and the wave turns around and comes back. So it's actually a complete reflection. So that's one of the reasons why it's been done since the 1920s, because it's reasonably easy to detect. You sweep the frequency, and now you're measuring at different altitudes on the bottom side of the profile, and you get funny things like the upper right-hand corner there, which you have to interpret a little bit, because as the wave is slowing down, time is not necessarily range, but you can work out then what the electron density profile is. These systems, again, were fairly large and complicated. You can see the antenna down in the lower right-hand corner there for a very simple CW swept tone. So what if you apply things like phase coding? Can you shrink the size of the system? Can you turn down the power? Well, that's something called emphasis. And the idea is not only can you turn the power down, you can use coding to help your power budget, but if you make something called a vector sensor is 3 electric field components, all orthogonal, and 3 magnetic field components, loops. Any electromagnetic wave, if you've measured all three E's and all three B's, you have all the information about where that wave is coming from. If you cross-correlate E with B, anybody who's done, gone through your electromagnetics course will know that that's something called the Poynting vector, and in that direction, the correlation maximizes. So on the upper right-hand corner, you can actually localize the return, rather than just grabbing any return and not knowing if it came from there, or there, or there. And so that extra dimension allows you to do the three-dimensional structure of the ionosphere at the reflection points, which is something that was harder to do. So you then do that in more than one station, and you can distribute these measurements. So you can start making velocity vectors with a much smaller system, with some limitations, obviously, than the larger one I showed you a little bit earlier. So this is something that we're pushing. By the way, the transmit loops down there on the bottom right-hand corner are electrically small loops, about 1/10 of a wavelength, and we're using those as our transmitters. But again, this is common distributed radio technology for all the EDIS fans in the room. Those are, in fact, the SN series software-defined radios. Up on the top there, those are X300s, for example, with some RF plumbing, mini-circuit amplifiers, and an octa-clock to distribute 10 megahertz locked precise time for the sampler. That's the receiver part. On the bottom is the transmit system. Again, one of these sort of loop transmitters, swept in frequency with the tuning operation, and then an N200. Anybody know how long the N200 has been around? A long time. I think it was first introduced in like 2003 or 2004. At HF frequencies, it's wonderful. So we use that as the pseudorandom code generator at the carrier frequency we'd like to use, and then we have a tunable antenna. So the right is the prototype. The left, by the way, are some examples of the antennas out in the field, and you can see that the bottom left one is at Ryan's house in near the coast of Massachusetts. I have one in my backyard, a little bit 15 minutes north of Worcester. And we just receive, all the combinatorics from the transmitters that illuminate the region around New England. But in the middle, though, is where we're going. We're using an, Xilinx RF SoC. You can see the board right there. And we're programming the FPGA using something called the Casper framework, which those of you in the radio astronomy community will recognize that's a sort of an idea to have an FPGA template for doing, for example, fast correlation. And we're basically taking we're synchronizing the samples using 100 gigabit per second backplane. And then the idea is to process that using NVIDIA Jetson and the whole Holoscan framework. It's been referred to more than once at this conference. But the idea is you can put this out in the field and you can send it back with packets on the Verizon cell phone network, because you like to put that out somewhere. We're experimenting with adding other measurements with some more timing boards, but that's sort of in development. This has been funded. Ryan's funded through a Young Investigator program at the U.S. Naval Research Laboratory, so this is, again, a partnership. Like everything in our field, it's always a partnership. Software stacks, this is what we use. On the top for receiving, I mentioned NVIDIA Holoscan for sort of scale processing. On the left is the Casper logo. That's, again, the FPGA fabric. And on the right is digital RF is a container format which we have released open source that we've been using, which is basically a time-coherent way to read chunks of samples without worrying about which file they're in and doing all the mathematics and the bookkeeping about finding that as the user. You just want to get your samples and get on with it. Radio Conda, I'll talk about in a minute. That's the receive side. For the transmit side, the stack has GNU radio in it for doing the pattern generation, and as we mentioned, EDIS radios. And then for telemetry and other kind of metadata, we're using Telegraph, we're using MQTT messages, and we're using an InfluxDB to grab all it. Sometimes Grafana kind of wanders in here to do visualization. That's very nice. So if anybody is interested in playing with this, I will recommend Brian's work on something called Radio Conda. This is a very nice packaged installer for GNU Radio and all those other packages that you see on the right-hand side. It works in Linux, it works in Mac, it works on Windows. The idea is, batteries included. You'd like to be able to not recompile GNU Radio all the time. So at least as long as Ryan keeps up with this, which he's certainly trying to do, this will just work out of the box and get you to playing. It's in the Conda framework. You are probably familiar with Conda, one of the many ways to do it out there. Conda Forge is a very nice environment. This is not just for Python. We primarily use it for Python, but it's not just for Python. And by the way, it's Not as slow as you might remember. I know some people in this community tried to work with Conda before and it was a little slow. It's gotten much better. So the idea with this particular distribution is build GNU Radio so you don't have to. And we are open to contributions. So anybody out there that has an OOT module, write to Ryan and we might be able to include it if you think it would fit in the radio ecosystem. So I really encourage you to look this up. It's really nice. It just gets you to playing pretty fast. And so the last thing I will mention, and again, small, is what if we could do radio telescopes with that 8-foot C-band dish? Anybody remembers, if you're back a certain long? This used to be the way that people did satellite TV, right, before we got the 18-inch direct TV dishes. If you take that and you build your own feed, which we have instructions for, you can actually end up turning that into a decent radio telescope for doing things like galactic rotation. You can watch the neutral hydrogen in the galaxy rotate. You can see the one Doppler shift going away and the one going toward if you you look long enough. You can measure pulsars, for example. You can watch them blip. You can even do interferometry if you have 2 of them. And it's all a GNU radio flow graph, and behind it, which you can see in the lower right-hand corner, and on the lower left-hand corner is a nice little Python dashboard where, for example, the operator, you can point to a particular source, which is preloaded, and the antenna will go there with a nice little alpha SPID controller and do the work. So we use this for educational purposes, demonstrations, but it's a perfectly nice platform. There's about 500 of these telescopes kind of scattered around, all in various stages of upgrading to this front end. So you go to the QR code or the website, you can watch that space. And finally, I want to give a forward reference to my colleague, Christina Collins over there, who's going to be giving the keynote tomorrow. We're also participating in a very exciting citizen science project that has developed over the last few years, something called HamSci. You can see the goals of HamSci right there. And I know Christina is going to talk about a lot more of the applications that the community has been able to do. This has really gotten a lot of eyeballs at places like NSF and NASA because it's a really engaging way to get citizen scientists to work with professionals. And what community am I talking to? I'm talking to a community that are implementers. You guys are tinkerers. Marrying you with the people who really understand how to do the science and understand how that measurement, like the ones I showed you in the last part of this talk, might be a little different than the larger professional systems, and working side by side with it is really, really powerful. And it is pretty amazing what you can do with a really simple measurement. And again, I encourage you to come tomorrow to hear more about that. But the idea is, we're working together in a larger community. It would be silly just to try to do things over here and try to do things over here and not collaborate. Winding all the way back to the beginning of my talk, the Event Horizon Telescope image would never have shown up if we didn't cooperate on a global basis. This is yet another form of it. So there's a very nice growing community, and I encourage you to get involved in that after you all take your amateur radio license exam, for those of you who haven't, whenever that is. I think that's later. Maybe. So that's where I'll conclude. The whole reason why we're still doing this work, the thought I will leave you with, is that our planet and the universe beyond are quite dynamic. We've been hacking at some of this for more than a century. We're basically at the bare start of discovering the behaviors and understanding what they mean for our society. This is really essential for us to move off the planet into lunar orbit, beyond into the solar system, or even into low Earth orbit, as is already happening as you and I speak today. So thanks very much for the opportunity to talk to you, and I'll be around.
I'm just wondering if you collaborate with the International Space Station, things that seems to be in the middle of that range.
It does. The ISS we tend to, as a community, we tend to collaborate with the ISS in a couple of different ways. It's a very nice platform to launch CubeSats. You can actually take a little CubeSat in a suitcase, hand it to one of the astronauts, it gets up there, and eventually they go out in an EVA and they launch it. They go like that, and it just kind of flies away. If you like something about in that lane, or in most cases, I hate to say, they try to throw it upwards so that it doesn't really necessarily always stay in the lane. The other way you can do that is the space station is flying around and it's actually going through the electron density at 350 or 400 kilometers. And so if you stick something called the Langmuir probe out beyond the sheath of charges that this station is gathering because it's a charged body, you sweep that You basically do kind of a curve trace. You sweep voltage, you measure the current coming back. You can fundamentally relate that to the electron density and the electron temperature. That goes all the way back to a guy named Irving Langmuir from the 1920s, who pioneered this for General Electric's research laboratory, trying to figure out how to make transmitting tubes more efficient. It's a fundamental property of matter. So we take that data also and use it. The other way that we're trying to collaborate with people that are having things in LEO like the International Space Station is, again, try to understand the environment that they're in and how it's changing and where some issues might arise if things keep on going the way they are.
Hey, yeah, thanks, Philip. That was a great talk. Just wondering if you see the INO sound eventually being completely replaced with emphasis, or is it something that, yeah, where are we at?
Right. So what we see, so, you know, ionosons, as I mentioned, as Greg referred to, have been around for more than a century, but they've been really simple devices. They've been transmit a CW signal, turn it off, wait for the pulse, move on, sweep, sweep, sweep. Using phase codes, okay, and then using directional antennas. I think eventually the community will gravitate toward that, so yes. But it is a bit of a paradigm change, and it's going to take a little while to do that. But we are still woefully undersampled when it comes to the upper atmosphere compared to where we'd like to be. So in some sense, I find it really exciting to have distributed networks of lower cost things that are measuring in a very different and more dense way alongside the traditional ones. So I think it's an and.